telecommunications, optical, and wireless industries. They've got instruments for research and development, manufacturing, field test, installation, and maintenance that address 2.5G, 3G wireless, wireless LAN, the 802.11 stuff, 10 gigabit Ethernet with IP, Sonic, SDH, OTN, and a full spectrum of RF and microwave applications. So thank you to our sponsors, Ritsu. We appreciate it. So it's my privilege to introduce the keynote speaker this afternoon. My name is Alan Dixon. I'm the chair of the, well, until this morning I was the chair of the DAS Forum. But Jonathan informed me that I'm now the chairman of the HetNet Forum. So I think I've been promoted. Thank you. Trust me, your applause is too kind. But it's my privilege to introduce our keynote speaker this afternoon. I'm going to introduce Scott Semone from Verizon Wireless. Scott's a member of the technical staff out of the RF Maintenance and Engineering group there. Scott broke into the commercial cellular space in 1989 when he transitioned out of two-way radio and moved into 9X Mobile. Since then, he's held a variety of positions. He's been a mobile radio bench, cell site, and mobile switching center technician. He's been an RF engineer. He's been a systems performance engineer and a systems performance associate director. He's done this through a series of jobs that started with 9X Mobile, which became Bell Atlantic 9X Mobile, which became Bell Atlantic Mobile, which became Bell Atlantic Mobile International, and then transitioned to what we know today as Verizon Wireless. He's had experience in the DAS industry through his in-building experience was mostly affected by some of the work that they did with the tunnels into and out of Manhattan, New York Stock Exchange, and a lot of different multiple fiber microcell designs throughout the New York City area. His practical experience has come through field work as a two-way radio and cell site technician, and before accepting the in-building DAS position within maintenance engineering, he was on the same team for 8 years, focusing on the Alcatel-Lucent CDMA EVDO platforms, and recently introduced the LTE macro base station platforms. Will you please join me in welcoming Scott Semone?
Thank you very much. Watch that. All right, folks, thank you very much. Thank you for the introduction. Actually, before I get started, Woody, why don't you stand up? Woody's going to be my AV guy today, right? This is the smartest table out of the whole place. So Woody's going to be doing my computer as I do my computer. Thank you, Woody. I appreciate it. All right, so here's the topics that I came up with, and this changed. Tracy has been asking me for my presentation since the middle of last week. I told her Friday, and of course I spoke to 4 individuals who are probably in this room, and they were asking what I'm going to talk about, and I asked them, what do you think I should talk about? And I had to go back and redo the whole presentation. I had it all done on Sunday. I get to the airport, I run into another guy, and he goes, so what are you going to do the presentation on? I told him. He goes, well, you're not going to talk about this or that? And so I spent the entire plane ride redoing my presentation. So I didn't see anything about small cell, so we'll talk a little bit about small cell and where the maintenance engineering group sort of sees small cell, and it's actually good news. I don't think it's bad news, right? I keep hearing, is small cell going to kill DAS, and I just don't think it's so. Preventive maintenance, and then we're going to do a little PIM. We'll do like a review from last year, and we actually have a good example, and we've actually come up with some ways that we're sort of tackling this within Verizon to actually identify it, mitigate it, and correct it, and move on. So I'm trying not to bring a whole lot of problems, more solutions, and some different ideas. And then neutral host alarming, which is just a slide. So just a little background. So I work for the maintenance engineering group, and I mean that sounds like we're the guys who empty out the dumpster. We put the toner in the copy machines, paper, replenish the water bubblers. I mean, that's really kind of like what we do, but we do it, we're more highly involved with the network. So our function is really to be a support mechanism for the regional folks. So we, lots of one-on-one with regional folks. We're sort of like I don't know, tier 2 support, I guess. They can pick up the phone. Many times we'll just jump in a car, we'll pack up tools, drive out to their region, and actually try and solve a problem that they're having a hard time solving. And those are the best ones, right? When I hear some of these problems, I'm intrigued. I don't know what the answer is. I don't have the silver bullet, but I want to get out there and start investigating and start breaking this down. We also work closely with the planning organization, right? So we're constantly talking to planning to kind of get like what their vision is for the future, and then we have to start lining up with the vendors to make sure everything fits. For example, you guys all heard DRAN, right? Every time I talk to David Chang about DRAN, I'm like, what is DRAN again? Well, explain it, So it's like we constantly have to go, back and forth. And there's this, struggle, and somewhere in between we find this happy medium. So what you're looking at, this is a network advisory. And this is something that comes out of our group. So when we talk about in-building, we talk about the macro, space, antennas, RF. It's either going to be me or it's going to be Nick Cordero. And both Nick and I, we generate these network advisories. These are internal documents that the regions can use in order to get guidance. There's in this example here, we're talking about the introduction of putting in a test coupler in the in-building systems. We have step-by-step procedures, right, showing the actual test equipment that they use and the directions on how to actually conduct the test. Right, so we're just not putting this stuff out there without any direction, right? Even if it's the first time the cell tech is turned on his Enritsu, he can open up this procedure and start at step 1, and we just just walk them right through it. And before you know it, after they do that, 4 or 5 times, they're doing it on their own. And that's really what it's about. It's a little bit of knowledge transfer. Right? It's not about just handing the guy fish, it's teaching him how to fish. Better yet, fly fish. So, all right. Just another example, right? Most of my advisories, and you'll even see in my presentation, lots of pictures. I like examples. I think, that is worth 1,000 words, I guess. So lots of examples. We show, some like best practices when prepping cable. We look at antennas, examples of what PIM looks like or what a problem may look like, setup examples, how you would actually set up the test equipment and how it kind of fits into the overall measurement when they're actually out there taking a measurement. Okay? And also, while I'm up here, if anyone's got a question, if it, just put your hand up or get my attention somehow, and we can even tackle it, because I don't want to get too far down, because it might be a really great question. All right? Danny, no dumb questions. All right? So, okay, so I heard the data tsunami, right? That's really what we're talking about here. Well, when I look at this plot and I think about, I look at capacity, pole capacity models, things like that. I mean, I almost want to sit down. I wish I was smart enough. I wish I was better at differential equations where I could do a population model, where I want to see how many users I could put on a network and what's that one extra user I put on that just causes the whole thing to just fall apart, right? You have the harvesting, you have lots of fish, and you got fishing licenses, and you hand out one more fishing license, and now that species goes extinct, right? That would be cool to look at, right? But I'm just not smart enough. I don't have the time to really put it in to generate this. But what are we really talking about, right? So LTE really took off, right? Wireless data it's been growing almost exponentially. So we see a lot of growth, and all the wireless carriers are trying to just stay in front of this thing. Load balancing, we're going back to the basics, right? We're redesigning our cell sites. We're trying to reduce that adjacent sector, adjacent cell, interference. I mean, when we talk about LTE, when we talk about EVDO, CDMA, at the end of the day, it's really co-channel interference, right? It's the same carrier, just different digital information on there. When we talk about small cell, you're going to see a lot of small cell. Small cell is like the new hot buzzword right now. You're going to see it in 700, and I think you're going to see a lot in AWS. All right, we're starting to see products starting to emerge. We're starting to test these things. You're going to see start bubbling up. How do I see small cell? Well, right there. Right now, what do we do today? We take a 40-watt E-No-B. We have like a cell hotel somewhere off the stadium, and it's generating 40 watts. We're taking that 40-watt LTE carrier. We're putting it into an RF conditioner. We're knocking that signal down to something like 0 dBm plus 10 dBm. It's not 46 dBm. So all that heat is being generated in that box. We're generating BTUs, and that requires air conditioning, and it's really kind of wasteful, right? I look at small cell, and I go, well, I hear numbers like 5 watts, 1 watt, half a watt, 2.5 watts, 2 watts, whatever. It's a lot better than 40 watts or 46 dBm. So I see where we have E-No-Bs, we might be stacking small cells in that room. Okay, so I think it's got a good fit. Outdoor DAS, indoor DAS, no difference, right? I mean, it might be just the antennas are different. You might be using an outdoor rated antenna versus something that's sitting in a ceiling tile. Repeaters, huge, right there. DRAN, I put a question mark. I still don't see DRAN. I'm kind of like on the fence. It might have its place. I just don't think it's going to be within the first year or so, for sure. And then, of course, everyone's talking about it. Why are we all here? Right? I heard all the different wireless carriers. I mean, lots of in-building growth. So this is the new cell site. This is definitely the new cell site. Okay, so when I think about capacity, just going around here, I think the repeaters, probably the best low-hanging fruit out there. All right? I mean, it's always been, repeaters have always been kind of like a cheap, dirty way to get wireless into a building. But now we're finding that there's lots of users, and we're choking the macro network. I mean, we put in a repeater, and now we have a sector that's immediately blocking, right? Most people are using their devices indoors. All right, so now the folks that are out on the street level, they're really kind of being choked by the repeater, who's actually serving the in-building user. So it's pretty obvious. It's a good, easy way to go. And I'm even going to talk about where's Rusty? The guy from Camden. Is he here still? All right, we should change Rusty's last name to Bolt, like Rusty Bolt, because when I heard him say like LMR 400, I'm thinking, oh, braided cable, I'm thinking PIM, and so I want to say to Rusty, like if he's installing this stuff and he's pre-wiring, definitely pre-wire a piece of coax to the top of the building, because you're going to need a GPS, because again, I see a small cell. If these things are really going to be cost efficient, like everyone's talking about, that seems like a good solution for maybe what he's looking for. So you're going to need GPS. And we'll even talk about that. But try and stay away from the braided cable, N-type connectors. And I know this stuff is low power, but I have a couple slides on that as well. So we'll even talk about that. Indoor DAS, outdoor DAS. We see a lot of these small cells. We think we're going to be hanging them on facades, building facades. We're already doing some trials on light poles. We're trying to find a zone that we feel that we can live with, where our cell techs can actually get to the equipment safely. We don't want to build out an entire network and then have to rely on a tower crew to fix everything, because it's up and out of the way. There's also the concern with the the primary wires and things like that are on these utility poles. And then Wi-Fi, Wi-Fi is one of those things that Verizon Wireless, you have Verizon Corporate and Verizon Landline. Verizon Landline loves Wi-Fi. Verizon Wireless, we kind of look at Wi-Fi like, well, the whole reason why we're doing these in-building systems is, right, it kind of competes with that almost in a sense. We don't look at it as a solution. When we actually build out our networks, we're kind of build it for the capacity that you think you're going to capture there, and build it without, build it without relying on Wi-Fi, all right? But a lot of these venues, they want Wi-Fi, right? Even though we're building a system, part of the deal is they want Wi-Fi, and we're happy to, build it and give it to them, and we just don't know how to maintain it. Right? So we're a little unfamiliar with it, but we are looking at tools internally to sort of tackle Wi-Fi. And part of that is, am I all right here? Okay. Part of that is just listening to the earlier discussions. If a Verizon Wireless customer walks into MetLife Stadium during the Super Bowl next year and they get a splash page and it says Wi-Fi is provided by Verizon or Verizon Wireless, even if it says Verizon, they're going to associate that with Verizon Wireless. And we want the customer's perception about our company to always be, held very high. So if the Wi-Fi is causing customer complaints, well, you'd be for sure our group will probably grab it, choke it, and figure it out, and we'll figure out how to best deploy those systems. But right now, we just don't have the experience within my group, and like I said, our direction is always think about CDMA, EVDO, and LTE, of course. All right, and we have lots of different frequency bands to do that. How am I doing? There's no way I'm going to get through this. I'm on slide 3. So I took this picture from one of our advisories, and really what I'm just showing here is how to conduct a donor to serving antenna isolation test. This is one of the reasons why repeaters generate interference. So we actually have a document, and we even say, give it to everybody, because everyone is doing this wrong. So anyways, so what I'm showing here, you got the donor antenna, which is typically out on the rooftop somewhere, looking back at the donor cell. You got a repeater box, and you got your serving antenna. And that piece of coax coming out of the repeater could be going in through just a single antenna. It could be going into a 1-to-2 splitter that's going off to 2 different antennas. It could be going into a DAS head end that's fed optically and feeding the entire building. All right, so that's how we kind of look at it. When we want to transition to small cell, like I said, we kind of look at this as this is low-hanging fruit. This is easy stuff. Well, what do? Well, we get rid of the donor antenna. We use that same piece of coax that's feeding the repeater from the donor, and we put our GPS antenna out there. Okay? Ethernet comes in, plugs in, and the RF comes out of the small cell and into the DAS head end. All right? Nothing changes. It's almost plug and play. All right? So that's how we kind of look at small cell. We think there's a lot of opportunities out there for small cell. Repeaters, they're probably, again, we're going to be, harvesting this stuff out of the network and pushing it out. Same thing with the in-building systems where we have these huge ENOBs that is causing us all this, or costing us all this money in air conditioning. We're going to probably harvest that stuff out. They'll go to the cell sites in a macro type design, and there'll be a wall of, small cells. When I go to these DAS venues and I look at, like, a lot of times it's Verizon, AT&T, we're right next door to each other. And I see AT&T, they use a lot of the remote radio heads just hanging on the wall, which is the same as what we're doing, except we're just using an ENOB cabinet. I imagine when we're done getting out these ENOB cabinets, our side of the DAS hotel room, if you want to call it that, the cell hotel, is going to look a lot like the AT&T. Maybe not instead of a remote radio head, maybe it's just a small cell. But that's basically the same concept. All right, so talk a little bit about preventive maintenance, and I talked about this last year, and I had the opportunity of traveling with Glenna, and there was a team of, 6 of us, I think, or 5 of us. Maybe it started off as 6, and maybe it ended with 5 or 4, I don't know. But what we did, we actually just got to travel the country and look at a lot of different large venues. And we wanted to kind of get a feel for what are we doing well, what are we not doing so well, what third-party companies do a really great job, and which ones don't do a really great job. And you'd really be surprised. I mean, I have tons of pictures, and I can't even go through them. But you would be just horrified by some of the rookie mistakes that are out there. And it's sad. We were talking about having some type of training, or, I mean, if you don't know that you can't put an antenna behind a steel pole, I don't know. I don't even know what to even say about that, I wouldn't let that person wash my car, all right? Because they'll somehow mess that up, all right? They'll use sandpaper or something, I don't know. So when we talk about the preventive maintenance, I mean, real simple up front, just start off right out of the bat, right? Specify components that all meet the PIM specification. And at some point I want to stop talking about PIM, and I say it every year. I'm like, I hope I don't have to do another PIM presentation. But every time I go out to these brand new systems, I see a lot of this stuff, and we test it and we find noise, and it's PIM, and I'm just like, gosh, I wish there was a way to get it out there, So this is why I'm up here, to kind of talk about it and get it out there. So if anyone's got any questions about this, this is the place. Work closely with property owners, right? Talking about antennas. I have a couple slides about antenna location and how PIM, from an external standpoint, really can wreak havoc on these types of systems. On-site construction, when you're building, test these things, right? This is where we find PIM, is when you're fabricating the connector to the cable, all right? That's it. It's that simple, all right? This is like plumbing. Right? With plumbing, though, it's easy, right? You turn on the water, and if you leak, well, you got to go back and redo that connector, right? In this arena, they just connect it, and they turn it on, and we don't see the leaking until later. And then we got to go back and troubleshoot it, and that costs us more time and money. I wish it would leak. I wish something would come out of the cable. Let's see, troubleshoot and correct, right? So again, just because it looks good, looks like it's connecting. I know some people, one guy told me he just pulls on the connector to see if it comes off. I'm like, that's what are you testing for? I mean, if you're using it to, I don't know, pull your boat out of the garage, I don't know, maybe that's a good test, all right? But not for what we're doing here, okay? And then we have this DAS qualification phase, right? So we're trying to work with these third-party integrators, even for ourselves internally, and then even with the other carriers as they're building these systems. Trying to come up with some language to kind of get an opportunity to get in there and do some testing before we actually connect up to really see that this is a system that we want to jump on, right? It meets the minimum requirement, and so we are working towards that goal. This is just showing, you'll see another slide, but you'll just see, these are just all the passive components that make up a typical DAS, right? You got a jumper that comes from the E-Node B, goes into an RF conditioner or a DAS tray. A lot of fiber optics, we don't worry about that stuff right now. You got these splitters, more coax going off to these different antennas. This is what I'm talking about. These are the passive components that make up this, the DAS, right? The distributed antenna system. I think that's what it stands for, right? Okay, so what am I saying, right? So, well, you can go into these systems at 20 watts, and even with the antennas, you should be doing better than minus 140 dBc. Without the antenna, meaning if you terminate these ends with a load or a PIM load or something that somewhat resembles like a good, healthy antenna, you should be better than minus 150 dBc. And we're constantly looking at this, right? Because I always say, well, God, even though the system is going to be built and designed, and at most we might be putting 2 watts into the system, why do I have to test it at 20, right? Well, it's like, oh gosh, I don't know. If you hire a roofer to put a new roof on your house, let me ask you a question. Is it okay if it leaks just a little bit? Right? It's not. It's not okay, right? We're paying to have something built. We want it done the way it should be, and that means, good connectors, and everything should be torqued down, it should be tight, and at the end, it should be a finished product. That's really what we want. How are we doing there, Woody? You all right? Okay. All right. So, yeah, I know. I saw you. He's texting, and you're falling asleep. He's probably texting you, and you don't even know. So, is this boring? Should I just move on? Something else, right? So that's what I'm talking about. So we actually set up a mock thing, believe it or not. We just lay out some coax, and I just started looking at this. I go, all right, 20 watts. You go into a splitter right there. A lot of times, it's a 3 dB hit right there. Sometimes it's 6 dB. Let's just say you're going into a 1 to 2 splitter. What happens? 20 watts now looks like what? Going down each leg. 10 watts, right? We just cut the power in half by 3 dB. So 10 watts, and then by the time you get a little further down, you hit one of these other splitters. There's another 3 dB, right? Before you know it, you're 5 watts. You're down in this really low power. And what we actually did is we actually took PIM sources and we put them out at the antenna locations. We put them right on the other side of the splitters. And it's real easy to pass this test. This isn't hard. This is simple. But we have to avoid some of the more obvious stuff, and we'll talk about that. I spent a lot of time on that slide, and that was, So, all right, construction phase. I think I talked about this last year. You'd be amazed how many tower crews and integrators I talked to. Oh, yeah, we got torque wrenches. Well, could you go out and get one? Oh, well, that's back at the shop. It sounds like it's behind glass or something. They only pull it out when they really have to. Everyone should have a torque wrench. Everyone. I have 5 of them in the back of my truck. Because I'm always looking. I have an N-type. I have a 7/16 Stin. Torque wrench, please. All right. This is again simple stuff. They make it simple. It takes all the guesswork out. What we find is if you over torque a connector, it generates PIM. If you're loose, it generates PIM. Torque it, doesn't generate PIM. That's the way I would go. What are we talking about here, right? So PIM, return loss, right? Bang it out in the beginning. Figure out what you're doing wrong at the beginning of the construction phase. You don't want to build out 100 different lines and realize that the guy who's been putting on connectors has been doing it wrong, and you got to go back and redo it. All right, that's not money well spent. Think long term, right? Attention to detail. I have some photographs of. We went out to San Diego, probably one of the nicest DAS systems I've ever seen us build. Really, really nice. So I took some pictures, and I kind of felt like that region did pay attention to detail. They did a great job there. And we found PIM. So even despite all the great work that they did, we actually found a problem. We'll talk about it, but again, it's a good story at the end. Exceptional craftsmanship. Again, the people that you're hiring, make sure that they're trained. I know in Verizon, we have a directive that you use the compression type PPC connectors. Is it called PPC any longer, JMA, or what do you call the connector company? JMA, okay. So we use these compression type connectors. And part of the directive is, I mean, you know, JMA, they support the tower crews. I mean, if they have a problem, they fly a guy out there and show them how to put these connectors on. There's free training. This is the stuff. All this stuff's free, right? Go out and get it, get qualified, understand it, because it's coming, especially if you're doing work at Verizon. Maintenance, again, you know, I'm asking our own guys when they do these site walks, put these boxes where our cell techs can actually get to them, not up in a ceiling tile 15 feet, you know, because we're not bringing ladders into hotels. They're not going to have that. Put it in a closet somewhere where it's up and out of the way. Make sure that it's plugged in and it's secured, the power is secure. You know, you'd be surprised. You know, we used to have a repeater that would go off the air every Tuesday and I think Thursday. Well, the cleaning people would come in, and then the person that ran the vacuum cleaner needed a plug. So they would unplug our repeater, plug in the vacuum cleaner, do the floor, and then plug the thing back in, but she never configured it back to come back into service, you know. We had to teach her how to do that, you know. So, and then the other thing here, plenum, right? So when we talk about in-building NFPA, I hear a lot of public safety stuff, right? It's hollow core, right? It's air core dielectric. No hacksaws, no anything, right? Use one of these plumber cutting tools. It's a real clean cut, doesn't leave any burrs, you don't get any of the little debris getting into the cable, because all that stuff will generate, guess what? PIM. Who said noise? No. Okay, so here's a step that we're, so Verizon, we are looking at, we're not even looking, we've decided we're moving in this direction. So we're going to switch to this 4.1-9.5 RF connector, and it's also known as the mini DIN. Clearwire did a lot of this stuff on their remote radio heads. It holds up against water ingress. It's got a good torque specification. It's like a 7/16 DIN, but it's closer to looking like an N-type connector. Honestly, when I look at it, you know, from the outside, it's hard to tell. All right, we're not expecting this to be next week on all your equipment, but any new iterations and you see an opportunity to change out that bulkhead and go to mini DIN, this is what we want to see. And this is to replace, again, the N-type. We see a lot of issues, N-types loosening up. We see people over-tightening them, and that's always a problem, okay? Again, just talking about some of the specifications, but here's the nice thing, right? So the N-type footprint, like a bulkhead, if this is on the output of your radio, your remote radio, on the output of your antenna, whatever it may be, it's a good match, right? So there's no loss in real estate there, all right? And we're actually starting to see this take hold. So, you know, 7/16 DIN, right? It's too big, all right? You're not going to fit it in a lot of these multi-band, multi-carrier type radio systems. You just don't have enough real estate underneath the box. We like this even for like antennas that are going to be kind of maybe hanging in an overhang where they're sort of exposed to the environment but not highly exposed, right? I mean, I feel just as good with a mini DIN as I do with the 7/16 DIN. So it's a good connector that fights back water ingress. All right, so you're not going to have that issue from a you know, return loss standpoint or failure standpoint. Here's just a close-up picture, just showing the differences. Here's the N-type, here's the mini DIN, and here's the 7/16 DIN. And really, what you're looking at is just the outer conductor. Now, it's just a little bit more robust. It's not as robust as this, but again, we're in building, we really don't need it. And even like if you're talking about an antenna that goes like in a ceiling tile, right? I mean, being able to come in with a nice piece of like, you know, half-inch superflex or something, it's not going to put a lot of torque on the ceiling tile. It's not going to put a lot of torque on the antenna. You get a good solid fit. There's a torque setting. You just hold the antenna, you torque it, put it up in the ceiling tile. It's not going to ever come loose. And with everyone talking, I hear Wi-Fi, I hear this and that going in. Everyone's pulling Cat 5. They're pulling it out. They're running fiber. I mean, these antenna systems have to like really put up with a lot of abuse. Right? I mean, you know, the contractors, they come in, they see stuff. It's not their problem, not their job, it's not their cable. They're going to push it out of the way. They're going to maneuver it any which way. It's going to make their job easier to get the next, you know, cable reel in there, whatever it may be. Okay. These are the pictures from San Diego. Stadium actually just gave them temporary space and they wanted to put it somewhere else. And I was really, really impressed with how well of a job they did. So we'll just kind of just blow through this. Neat, right? I mean, you can see the craftsmanship. You can just see how neat everything is, how well organized everything is. Here are the RF conditioner trays that we talk about. You hear that a lot, these RF conditioners. We see AT&T uses these. We use them. Here's the back side of it. You can see what we're doing. High power coming in, and then you see all this low power stuff. If you're doing low power, it's that when you're on braided cable at that point, that's okay, right? Because now you're down at like 0 dBm, plus 10 dBm. You're really low. We think that half a watt area. Actually, no. I actually take that back. 20 something dBm is we've seen problems there. So we'll talk about that. Labeling, right? When we talk about the troubleshooting exercise that took place out in San Diego, right? I mean, having these labels and being able to just quickly look and just know where you need to go really just makes troubleshooting just so much easier. Power plant, when I see this, I think the Superdome, I think the Super Bowl, right? I mean, we all know what happened, right? There was a blackout, and everything was backed up on battery. It just kept going, kept processing calls. What we did notice is people stopped, doing whatever they do during a football game, like texting and sending pictures. They pick up the phone and they call their loved ones and say, everything's all right. That's what people want. We see that during Hurricane Sandy, that earthquake that hit, what was that, the Washington area. I mean, people don't want to text any longer. They want to pick up the phone and actually speak to their family. The recent bombings in Boston, people want to pick up the phone and make a phone call. So there's this balancing act, right? We always talk about data and this huge capacity problem that we see. But then if we start allocating all this spectrum to data, well, what happens when these other events happen? And now we choke the network from a voice side. All right, so there's this constant balancing act that we are always maintaining. I mean, we have scripts to do one versus the other. Right? We can have a CDMA carrier sort of sitting as a 3G1X carrier or voice, and we have some scripts that we can run that actually helps migrate those carriers over so that they handle voice traffic better than the current configuration. Remotes, more closets, more pictures, more neatness. Again, just this fiber optic cable hanging out of that tray, probably not a good thing. A little preventive maintenance that could be cleaned up a little bit. Okay, so the earlier example, I talked about the advisories, right? So this is a network directive. So that advisory, we introduced it probably about a year ago, and then it was upgraded to a network directive. So the difference between a network advisory is we highly recommend it, all right? Which means just do it, all right? I don't know. The directive says, well, you got to do it, right? Because we had it out there for a year. We went out, we looked at some new systems, and nobody was doing this. So, all right, well, now you have to be told to do it, right? And we see a lot of value in it. So surprisingly, San Diego did it, right? It was a Corning mobile access system, and this is an MA 2000. This is the same system that was at Lucas Oil. And I was working side by side with the AT&T guys, because when we were turning up that system, I mean, we were literally like a week or two before the event, and we were literally just turning on LTE. So we had a good handle on what we were doing from taking an LTE measurement. And the AT&T guys were kind of like, well, could you come out to the remote end and see what we're doing and compare? And because we were splitting the power at the amplifier. And I was just like, I was saying to the Corning mobile access guy, do you have like a monitor port, something I can plug into and see what's going on without interrupting this RF connector? He's like, no. I'm like, we got to do that, right? So we came up with this little bulkhead. So you pop out the connector, the existing connector that's there, and you put in this coupler, and it just kind of extends the cable. And so these are the kind of the ideas that I'm looking for the other DAS providers to kind of get into their overall design. At the end of the day, if you're buying filters, all these multi-band, diplexer, triplexer, whatever you want to call them, just have them integrate a little probe in there so that we can go in there and take a measurement, minus 40 dB down. It's real simple. But so what was kind of tripping us up when we were doing all this troubleshooting was when we would disconnect from the DAS. Well, the mobile access stuff would see high VISWAR. and it would shut the radio down. So we disconnected, we hook up our service monitor, we take the measurement, and we're like, I don't see anything. So now, and these remotes, they're always, it's always a 15-minute walk all the way back to the head-end room, and the guy who's at the head-end room not answering his phone, so what should have taken, 5 minutes took, 5 hours, is what it seemed like. So we really like this. Going forward, we want to see test ports, couplers, all right? This allows our field engineers, this allows other tenants that are on our system to be able to go on site, take a measurement unobtrusively. They're not interrupting service, they're not causing any downtime, it's not service affecting, and they can look at their carrier, they can look at their information and make sure that they're calibrated or the levels that they're putting out are the expected levels, all right? It's really, that's kind of like how we think in maintenance engineering. Remote power, here's an example. There's a test coupler on one of the outputs of one of the smaller radios. And again, the field engineer just comes in with a little, I think it's a QMA connector, pops it on there, and he's 40 dB down. He sets his service monitor, and he can demodulate the LTE, EVDO, or CDMA carrier. It's that simple. Doesn't interrupt service. I don't know. This just sells itself, I think. I don't know. Does everyone agree with this? Yeah? Okay. No, Woody? You're shaking your head no? Okay, he's SIDAC, all right. Okay. More examples, right? So within Verizon, we try and put some products on the table, and we let the regions kind of pick what they want to buy for their field engineers, right? So I think this is sponsored by Anritsu, so I guess we could point out the Anritsu box. There's brand A and brand B over here. But again, another network advisory, right? We put it out there, and then if you go down and look at this advisory, we have step-by-step procedures for each of these boxes. So regardless of what the field engineer has, there's a good procedure to at least get up and start taking a measurement. Even though if they don't even understand the results, they can email the results to us. We have some automated test that says, pass or fail. Screen stays green if it passes and turns red if it fails. They can pick up the phone and call us and say, hey, I'm getting this failure. Couplers, good. All right, so this sort of supports this. This supports that. All right, you need these two things in place to, there's no sense in installing these if you don't have this. All right, so we do a good job getting the equipment in our field engineers' hands. All right. How they use them, that's a different question. Sometimes they come out, go get your service monitor. They get it. It's like brand new. It's still in the shrink wrap. It's got those moisture packs still in the box, So we're going to talk a little bit about antennas. So I've seen some really cool stuff. This is an example of the CSS antenna, the True Omni. What this allows you to do is install this thing up and recess it up inside a ceiling tile. I know if you go, I saw one out at the Galtronics booth. They have a very similar design that, again, there's like a plate that gets installed in the ceiling tile, and the antenna sits above the ceiling tile so that there's just a very little profile of the radiator, the radiating element that's below the ceiling tile. The truth is, my opinion, you put the antennas above these drop ceilings and never see the antenna, and it'll propagate fine. We don't see a lot of issues there as far as scatter and clutter. All that stuff is in the office. The part that does concern us, though, is things in the near field from a PIM standpoint. All right, so, and again, we're going to talk about that. More antenna placement within the stadium. And a lot of these stadiums, they don't want to see the antennas. Unfortunately, the way these stadiums are built, it's kind of hard to hide them. And they want really great service, but they don't want to give us any antennas. And there's just struggling. We go back and forth with some of this stuff. Okay. So let's talk about, we're going to talk a little bit about PIM, and there's no way. So, all right, so low power. So this comes up a lot, and I would say even last year, I'm always a little unsure when I talk about this topic, but it's always worth exploring, and that's what we do. This slide here is actually courtesy of Tom Bell from Anritsu and Rick Hartman from Kalis. Both guys compete in this space for selling PIM analyzers, but we're part of that IWPC, and we're looking at PIM and how it works in DAS. And this is a good topic, right? I mean, we do a similar I don't know what you want to call it, a forum, right? Internally within Verizon, it's called the IBTUF, or In-Building Technical Users Forum. And not to be rude, but when we looked at this presentation, I'm like, well, what's the title of it? What do we want to call it? And they told me the title. I'm like, how about PIM sucks, right? Because that's what I kind of got out of this thing, right? It's just a mess, all right? So in this example, what I'm showing here, right, minus 80 dBm. This is what the PIM analyzer is showing, and I think that's the third order intermod. I can't imagine it being anything higher in order. But worst case scenario, minus 80, and that's at 2 times 30 dBm. That's 1 watt, folks, and that's pretty close to where a lot of these low power DAS systems are at, right? I mean, when I know like some of these neutral hosts, some of these radio systems, it's Verizon gets 30 dBm and AT&T gets 30 dBm, right? It's a 2 watt composite amplifier. This is a problem, and this is more truth or more examples of that. All right, so a little good news, right? So we're playing with some absorbing foam. What if you can't avoid, right? The stadium, they're already locked in. These antennas are already in place, and the opening game is tomorrow, right? We're trying to play around with some different ideas, maybe put some foam, and we have some ideas why we think PIM happens in some of these low power cases. But you can see same antenna, same location, and a huge improvement just by putting the foam there. Small changes in just the location, just again trying to get whatever's in the near field. Oh, Rusty, you made it. Okay. We were talking about you earlier. Did someone text you? Oh, okay. So he's texting, he's nodding off, and you're on phone calls. All right. Okay, so right, just moving the antenna, getting it away from whatever's causing this PIM issue was huge improvement there. 700, not so good, right? And we'll talk about why, right? Well, why the difference. It looks like they moved the antenna. They tried different types of absorber. There's a new absorber that supposedly works a little bit better at 700. So I don't know if you would stack some PCS type absorbent material and maybe some 700 or some high band, low band absorber. A lot of the stuff that we look at is stuff that the military uses. Their surface ships, subs. They make all types of stuff to minimize harmonic or any type of emissions getting out. So this is the same stuff that we're looking at. We're just trying to tackle it from a different perspective. The problem is this stuff's expensive, right? It's like, you guys familiar? Anybody build or use or have like an anechoic chamber on your facility? Right? I mean, yeah. That foam, that stuff's expensive. The anechoic material that you put in those chambers. So why? Why did we see this really great performance in PCS and really poor performance in the 700? Well, again, we're just kind of hypothesizing at this point, but we're thinking maybe the back lobe of within the near field of the antenna. We think that has a lot to do with it. What we did find, we actually tested some different antennas. So we got some small antennas, and we had some antennas that were bigger physically, right? And and of course, I don't know if you remember, but the near field changes based on the physical dimensions of the antenna, and things get better. So the bigger antennas actually seem to do a better job in this PIM-rich environment. And it might be just because we're talking about a bigger ground plane. That bigger ground plane might be directing more of that energy down, onto the floor rather than through these back lobes. We tried a whole bunch of different ideas as far as like lining the sealant tile with a foil. So we're still going to you're going to see more of this. Maybe next year, maybe we'll talk about this. So we'll have more answers. But I don't have all the answers at this point. But this is what we've sort of seen so far. Okay, so some kind of bad news, right? PIM is tough. It's going to be challenging. But like I said, just introducing PIM sources. You know what works if you want to test this stuff back in your lab or out in the backyard or wherever you're doing this stuff? Steel wool. Just go buy that old metal steel wool, wet it, let it get rusty, and that's a great PIM source. You just get within very close to the antenna, and you'll see your PIM analyzer go from a minus 50 down to like, minus, 100 dBc real fast. This is I've always done this. We're doing PIM training out to the different regions, and even with the tower crews. We would put an antenna, lay it on its back, and show that we can get a minus 150 in a parking lot full of cars. And then I would just take a handful of car keys. I would get like, the guy, he's like a janitor. He's got all the keys, like Schneider from the Super, right? And I'd get his keys. He's got, what are all these keys for? He knows what every key goes to. Anyways, I'd walk up close to the antenna just with keys in my hand. And what are keys typically, right? They're brass. They got nickel plating. What were the old RF connectors? They were brass. They had nickel plating, right? These are all bad things. You get up just within like a few feet of the antenna, and you'll see that antenna under a load or under a PIM test go from minus 150 dBc, plummet all the way down, minus 120, minus 115 dBc. Right? It's a great example to just kind of give you a feel for. You can have a really good antenna, but if the antenna is installed next to something that's rusty up on the tower, most likely it's going to be a problem. So again, PIM, right? I think we know why. The thing I want to iterate most on this slide is this, right? Well, so we are more and more getting pushed into doing these neutral hosts. I'm not saying a neutral host is bad. It's, in a perfect world, I would rather just have our own system and let everyone else have their own system, but the whole ceiling would be loaded with antennas. And that's probably not going to go over that well. And when I just look at just the frequency bands that Verizon has alone, right? So we got the 700, upper C, we have the cellular band in almost every market, we have PCS, and now we're looking at AWS. I mean, that's a neutral host just in itself. Just us alone requires a neutral host. Then you look at what AT&T has and T-Mobile and Sprint. I mean, so at the end of the day, what we have is when you bring all these carriers together talking or transmitting on the same antenna system or same antenna, you have a 24/7 PIM test running constantly. We saw this in the Big Dig. I worked very closely with the folks from AT&T and Verizon. During the busy hour, we were both complaining. We see really poor performance. Our KPIs, lost calls, throughputs, everything just blows up. And what it was, more traffic, more carriers come up, more power, and we were generating this intermod component that falls within our receive band. And that's really what PIM is, right? PIM just generates this, this noise into or these intermod products within the receiver. Now, the mobile devices, the UEs, whatever you want to call them, they're now challenged with trying to communicate with the cell through all this interference. And in data, it's different, right? If a symbol is lost, right, what does that mean? Retransmit, right? If I'm, you call me on a Saturday or Sunday, and maybe I'm out somewhere at my favorite fishing place, and there's not really great wireless coverage, and you say, what am I doing? And I say, I'm fishing on my boat, but all you hear is, I'm fishing on and you hear oat. You don't hear boat. Well, your brain doesn't go, what's he fishing on a goat for, right? That doesn't make any sense. Can you do that, right? Your brain says, oh, he's boat. Your brain put it all together. You don't even ask me to repeat it, right? Data, different, right? It's either a 1 or a 0, the correct symbol, the wrong symbol. And if it's wrong, if something didn't check out, send it again. And that's where these throughputs really slow down. Again, this was just a review. I put a couple slides in here. I'm not going to spend a lot of time on this. But again, just when we do a third order test in the cellular band, we use a channel that's in the A band, which is typically AT&T, and then we use a channel in the Verizon band. And Verizon and both AT&T got together and we talked about where these two channels should sit, so they don't generate interference to each other. And then the third order intermod, falls down here, but it falls within our receive band, so we can measure it. With LTE, here's our 10 megahertz LTE carrier. A phenomenon that happens with intermod products is you got the third order, you got the fifth, you got the seventh, the ninth, right? So the third order, well, is the bandwidth. It squats. It's about 3 times the bandwidth. So at 10 megahertz, well, now I'm looking at 30 megahertz worth of noise. 10 megahertz carrier, and you do this convolution, you have the bandwidth at the fifth order is I guess 50 megahertz. The math is right? 10 times 5. So the receive band, well, what's happening here? We're seeing the 7th and 9th order intermod. That's what's falling in our receive band. And I exploded that model to kind of show you what that looks like. So here is the 7th order, and here is that 9th order. And if you kind of look at the lower, actually just real quickly. So if you kind of look at the X and Y axis, this is frequency, and the Y is amplitude, if you kind of look at the intermod product. So what you're looking at here, right, so you're seeing the roll-off from the filter of the E-Note B. But at the lower end of the spectrum, you have high amplitude, and then you have this kind of decay, right? Same thing, high amplitude, and you have this kind of decay as you move up in frequency. This is what's really happening. This is what PIM looks like using a spectrum analyzer. This was, we learned this early on during the LTE trial. And this was, again, this was an E-Note B. This was at 43 dBm. We measured it. We saw this when we actually brought the carrier up to full power. We measured minus 125 dBc. Minus 125 dBc, the E-Note B is crippled. It's completely done. All right? No one wants to use that service. You're better off on 1X. All right, for sure. All right, so we're going to talk a little bit about San Diego. So we have our field engineers. We have a procedure out there. Go out and do these checks annually. So they go out, they look at the receive band. They capture it over time, and they say, that doesn't look good. I see a noise rise. I see a lot of extra noise, but LTE traffic looks like interference. But this noise rise here, this long trace, kind of starts to look a little bit like PIM. So the next step is for them to go out and actually bring the carrier up to full power and see what it looks like. Not from a reference standpoint. You're not going to go out with a PIM analyzer. You're going to use your spectrum analyzer and measure it from an absolute value, just like you would any signal in dBm. So they configure the E-Note B to 40 watts. 40 watts goes into the RF conditioner, gets knocked down from 46 dBm to something like 0 dBm, gets processed through the DAS head end, goes over some optics, goes out to a remote radio head, gets converted back to electrical, and this is what we saw. So this is the noise rise. This is what it looks like when this thing is at full load. And here's what's interesting, right? So the whole, we don't need to PIM test the DASs. We don't need to PIM test the antenna systems, right? False. I mean, this is a 20 dBm max output radio. And look at the noise rise it generates. Doesn't take a lot, and if it's close to the radio, a lot of these systems, they have an uplink, LNA, right? If there's PIM there, it's going to amplify it, and it's going to just send it right back to the E-Note B. What else does PIM do for us? Well, we've caught, I use the word caught. We've gone out to some of these systems that had to be set up real quickly, and we start going out there, we start optimizing, we start testing, and we see the throughputs are just not what they should be. So we start doing a little bit closer look. And what we find is we see this physical uplink channel. It always seems to be a little bit higher than expected. And what we think is happening is that the contractor, they go out and they see this noise rise, right? And they go, oh, that's not good. So then they'll attenuate the uplink. They bring the noise up so the noise rise looks flat. And they said, that looks better. And they leave it that way. Well, what happens is, because we have this unbalanced uplink and downlink, well, the UE starts to break down in the LTE protocol, how power control works, and we start seeing this stuff. So, PIM, high noise rise, right? We have a tendency to kind of start adjusting knobs, start adjusting attenuation values, kind of hide it, mask it, whatever you want to call it. And then we have this unbalanced situation taking place where the UEs are now broadcasting at a much higher power. And in a building system, right, well, we have a lot of adjacent sectors. So now you have this omni antenna, whatever they're using in these devices, now broadcasting and causing interference. And that's hurting what? Everyone else's throughput. Even interfering with the macro cells that are around these types of stadium. Don't give me that look, Woody. He's angry that he's got to work. Woody, why are we on a different slide? What's going on? There you go. All right, sight act, right? All right. So I know it's kind of tough to see. We got blue here, but that's sort of like what a normal trace would look like. And this is the problem, right? This is that unbalanced trace is what we're kind of showing here. And all we really did, we just went in, we wanted to go in and test this concept. We just went in and just changed the uplink attenuation by 10 dB. And sure enough, we're able to break the system almost instantly. We see the UE instantly react to this and then start creating problems to the adjacent sectors. All right, so balanced uplink, downlink, real important. And this is something that we're going to focus on this year. We talked about this a lot at IB Tough, and this is something that we're going to be looking at going forward. All right, so PIM mitigation. I have like 2 minutes to get through this. So detecting PIM, investigate the noise floor. We just did all this stuff, right? So again, possible PIM. He's looking at the problem. Right? At full power, definitely have a problem. We gotta go figure this out. So what are we talking about here, right? So he's going to take a measurement off of the actual ENO-B, looking at the uplink using a spectrum analyzer. We're going to be doing a lot of work with the RF conditioner. We'll talk a little bit about what that means. So what's he saying here, right? So disconnect the uplink cable from the RF conditioner tray associated with the path, right? If the noise clears, right, that means look towards the DAS, right? If the noise stays, well, then it's probably coming from the ENO-B going into the RF conditioner. So let's just take a quick look at that. So if the problem stays, that means that you have 40 watts coming out of your ENO-B and you're going into this RF conditioner. The problem's either at this connector or that connector. It's not the cable. It's never the cable. It's always the connector or the guy who made the connector or the guy who didn't torque it down, that guy. And then what I'm talking about is this uplink right here. So you could break that uplink, and if the problem goes away, well, then this is nice and clean because you would still have a PIM component there, right, Woody? The site act guy's fault, right? Gotcha. Okay. So if it goes away, well, now this is the problem, right? You got all this stuff that you got to go out and test, and a lot of these systems, right? It's just not going out to one antenna. It's multiple remote radio heads serving or simulcasting a very large sector, right? So there's lots of closets to go check. So, and there's lots of, all these red arrows are potential PIM problems. At least these have been my experience. Always a loose connector. It's always some component, rather than buying the $30 part, they bought the $15 part. And, okay, so again, labeling is important, but here in this example, right? So we got 1, 2, 3, what's that, 6? 5, 2, 4, 5. So we got 5 remote radio heads, or 5 RRUs, whatever you want to call them, remote radio units, feeding a particular sector. We know we have a noise rise, but we don't know which remote radio head. So one quick dirty trick is remove the optics one at a time and see which one is actually your culprit. And then once you sort of determine which closet it is, look at the you'll look at the the labeling, and that'll steer you to that closet. Now the next step is to move operations over to that remote area. You can see here there's a lot of great tools out there. You can set up your spectrum analyzer and broadcast it over Wi-Fi, and you can look at it on your smartphone. So you can actually walk out there while the spectrum analyzers are sitting back at the cell site and play around with this stuff. That's Dennis McCall from Southern Cal, and let's see, again, using the small handheld tool, and problem solved, right? It turned out just to be, a loose connector. I mean, it could have been a lot of things, right? It could have been this braided cable. I mean, we got lucky. I typically don't like braided cable, but again, right, when we talk about like low power, we don't think braided cable is a big problem. But it is a problem, right? This is a plus 20 dBm composite output remote radio unit. There's not a lot of power there, but still, we saw about a 12 to 13 dB noise rise. Okay. Are you saying 5? Are you saying now? Or are you saying stop? What are you saying? 2? Okay. 3? Okay. Okay. So I'm really on my last slide anyways, sort of. Okay, so the next topic, right, is, so I hear a lot about neutral host, and, I know AT&T's in the room, Sprint, others, right? So one of the things I kind of like about neutral host, I do like the idea of transparency. This is, I think I said this last year, right? So transparency, right? So one of the ideas I'm working on, and it's only because this is really what I want. It doesn't mean that you guys want this or the other tenants want this. But like what I'm working on back at Verizon is, so we use this site portal tool. And we use, it's very powerful. It gives us a lot of visibility to the DAS head-end equipment. It allows us to remotely dial in. We see alarms. We treat our DAS head-end units or these DAS systems just like we treat a full-blown macro network. And we should, right? Because this is the next base station. This is the base station going forward. All right, you're going to see little growth in the macro build-out. You're going to see more small cell, DAS, getting, because where are people using their devices? Woody? In this room, right? Inside. In that thing, yeah. At that table over there. So, all right. So what I'm trying to do here is, so let's just say this is a Verizon-owned system, right? We got, I don't know, MetLife, for example. And we have this site portal platform that we use. It's by the C-Squared folks. And here's Verizon sitting here. We have visibility to it. Our system performance engineers get, if something goes in alarm, they get it instantly. They get an email, a text. We can do a lot with it. It's real flexible. I want, if they want it, if, let's just say Sprint and AT&T are joining the system. Let's just say AT&T also uses C-Squared site portal. They would have basically the same thing that we're seeing, except they just wouldn't have the ability to log in and make changes. But they would see the same exact alarms that we're monitoring on our system. They could pick up the phone, they could escalate it if we didn't catch it, if our NOC missed it, whatever the case may be. If the other tenant A, doesn't even want to use site portal, they don't like C-Squared or whatever, they can have like a site portal lite. This is something that we would put on site that they could, if they wanted to have access to it, they could set that up and see, sort of a light version of these alarms. And same thing, they could escalate to whoever owns it. Hey, do you guys get this alarm? Are you out there? Big show tonight, or big concert, something along those lines. So that's sort of what I'm thinking. I'm thinking along these lines, and the idea is to develop it, roll it out there, and offer it, and then hopefully it's reciprocal, right? As we join, someone else's in-building system or neutral host type system, I would like to have a read-only feed to have that same type of visibility. So that's my presentation. That's really what I was really just wanted to talk about. Is that okay? Yeah. Okay. Oh, so. So I'll just leave this up here. That's my email address. If anyone, I know I went way over time, but if anyone's got any questions, you could always email it and just put in the subject. I don't know. What do you want to? Do we want to put HetNet now? Put HetNet in the subject line, and that'll direct it to my my deleted folder. And just go. Yeah. No, that's fine. It's real simple. It's always our name and whatever. Whatever. Yeah. So no, just shoot me an email. If I may not get back to you within maybe a couple days, but I always try and get back to industry folks that are asking this question. One guy who was here last year, we went back and forth. He actually wrote a really good paper that was presented to the 3GPP folks about PIM. So I'm always happy to kind of chip in and get that information out there for folks who are looking for further clarification. Okay? All right, thank you.
We're just going to have a quick set change here, so stay in your seats. The next panel is coming up, and it is on how to get a DAS from A to Z. For those of you who have been playing along with us as we tweet, our hashtag is DIA NOLA.